This far, we have seen functions that go from r to r squared. And this is what I mean. So far, we've seen r of t functions. So the input is t, one-dimensional, and the output can be two or three-dimensional. So we could have some curve going this way. So we're taking this and either stretching it or shrinking it and putting it into a three-dimensional space, sometimes in two-dimensional space. So we are going from a single r to either r squared, or in this case, r cubed. So we have this kind of function. Little r goes from the real numbers to the three-dimensional space. We've done this already. We cannot draw this in one picture because we need 4 dimensions to do that. We have also seen functions of 2 variables with 1 output. So here, in this case, we are going from r squared, xy is 2 variables, going into a 1 variable. So a generic picture is we have some kind of input, x and y points, and then the output can be drawn up here. So the output may look like this. Yeah. All right, so this is the output and this is the input. And in this case, we are able to draw the picture in the graph in one picture because we don't exceed 3 dimensions, 2 dimensions for the input, 1 dimension for the output, so that makes 3. Here we have 1 dimension for the input and 3 dimensions for the output, so we cannot draw that in one picture. We need 2 pictures, 1 for the input, 1 for the output. Here we can do that. Now, sometimes we have r cubed into r. Again, we would not be able to draw that picture because that would be we will need 4 dimensions to do that if we had r cubed into r. So we would have f of x, y, z, and then again, we wouldn't be able to draw that picture. So those are not neither one of those is what we would consider a vector field. A vector field, on the other hand, is a function of 2 or 3 variables where the output is going to be 2 or 3 variables. Yeah. So f of x, y, 2 inputs, is going to give us a vector, pq. And p is a function of xy, and q is a function of xy itself. So in a way, this can be seen as 2 of those combined. Yeah, pretend you have f1 and f2, so you would have 2 of those. But the picture is different. It's not quite related to that. So the input is the xy plane. The output, we think of it as the xy plane also, xy plane. So a point here will have an output. Oftentimes, though, a lot of people, even though it should be an output, a point, people think of this as a vector with a direction. Remember, a vector could be a point or a motion, depending on the context. So a lot of people think of this as a motion. So for instance, for this point, we can have this vector. For this point, for instance, I don't want to mislead you because I was going to do, well, let's do something that is a little flat. There you go. And then maybe for this point, we go horizontal. And maybe for this point, we go down. So that way, the position of the points and the corresponding outputs are not necessarily completely related. They could be very different. Yeah. So this is a function that goes from r squared into r squared. And whenever we have more than 1 in the exponent here and more than 1 in the exponent there, then we call this a vector field. Typically, we have going from r squared into r squared or r cubed into r cubed. Now, people have decided to draw this in one picture. Technically speaking, we need 4 dimensions, 2 for x and y and 2 for x and y again combined. But people have done this, and that's what they called a field. So vectors. So let me combine the two. So we can combine the two. The inputs, remember, these are the inputs, and those are the outputs. Up here, let me emphasize that these are the inputs, or the inputs come from that set, and the outputs are here. The inputs are here, and the output is the corresponding height for each one of those points. Okay, here we can combine the two. So if we have this point, which would correspond to this vector, we can just draw the point and the vector starting at that point. So this is the vector corresponding to this point. So we have both the output and the input in one picture, and that's what they call a field, a vector field. So this second point will have, for instance, and I'm just making this up. I don't have a formula in particular. I'm just pretending these are the corresponding outputs. So, and then this point will have a corresponding vector there, and then this point goes down, for instance, this way. So we have the input and the output, input and its output, input and its output, and you can do that through the whole plane. And that's what is called a vector field, or a field of vectors. You got a field of corn, or a field of strawberries, or a field of potatoes. So this is a field of vectors, I suppose. Let's look at a small example. Example 1. So we typically use the letter F, capital F, when we have a vector field, lowercase f when we have just a function of 2 variables with one output, and R is the one we typically use for going from one input into 2 outputs, a curve. So curve, surface, vector field. Yeah, so now we are going to focus on the vector field. So pretend you got f of x comma y equals x plus y comma x minus y. So in this case, we have p and q. When we speak about p and q, we refer to the corresponding coordinates of the output. So this would be p and this would be q. And I just want to draw this. We can make a table. The inputs are going to be vectors. The outputs are also going to be vectors, and we can just draw a table. For instance, 0, 0 goes with well, 0 plus 0 and 0 minus 0 is 0, 0. 1, 1 goes with 1 plus 1 is 2, and 1 minus 1 is 0. 2, 2, we got 4, 0. How about negative 1, negative 1? Let's see, that's going to give us negative 2 and 0, because we subtract one from the other. Negative 2, negative 2 gives us negative 4, 0. All right, so that gives us an idea of the diagonal. How about a 1, 0? Well, that's going to give us 1, 1, because 1 plus 0 and 1 minus 0 is 1, 1. How about 2, 0? That's 2, 2. That is interesting. How about negative 1, 0? That's going to give us negative 1, negative 1. How about the other way? 0, 1. 0 plus 1, 0 minus 1. So we're going to end up with 1, -1. Oh, that is interesting. How about 0, 2, 0 plus 2, 0 minus 2. Now, this is a very, very specific vector field. How about 0, -1? So we have 0 plus -1, so that's still -1, and 0 minus -1, so that's 1, and so forth. So you can do as many as you want to start understanding. So the shape, the graph of this, so 0, 0. Now, if you got 1, 1, you get 2. So at this point, 1, 1, you have this vector, 1, 2. So we got a vector that is reasonably long. 2, 2, which would be about here, 2, we have a longer vector. We go 1, 1, 2, 3, 4. So we got this vector corresponding to this point. We got 4, 0. How about -1, -1, -2, 0? So here we go 1, 2, there. And -2, -2. So about here is where we start. We got 4. 1, 2, 3. That's going to be outside the page. 1, 0, it goes with 1, 1. So 1, 0 goes with 1, 1. So sometimes the vectors are going to bump into each other. So this one bumps into this one, but that's okay. That's just the way the field behaves. 2, 0 goes with 2, 2. So 2, 0 goes with 2, 2. So about 1, 2, and then I think it bumps into this one, if I'm not mistaken. And how about -1, 0? -1, -1. -1, 0 goes there. So we have a mirror image. Well, it looks like a rotation rather from this quadrant to this quadrant. And then it looks like we have the same thing going here. This is an arrow. So we indicate the inputs with dots and the outputs with arrows. We're differentiating one from the other. How about 0, 1, 1, -1, 0, 1, 1, negative. So this one will point down this way. Boy, that's an interesting 0, 1, 0, 2, 2, -2. So 2, -2. It's going to go down this way, etc. Yeah. So you can see vector fields, pictures of vector fields in any calculus book. They are pretty neat. Sometimes they let me give you sort of a generic one. So that was the end of example 1. You can plot more, but just in general, yeah. A vector field oftentimes kind of looks like this: arrow, 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 and then maybe more arrows going this way and diverging and maybe coming this way. Oops, that's supposed to be straight. All of the arrows are supposed to be straight, but as they move, they change direction. So a lot of vector fields look like this. So they follow some direction there. And so they're really good at modeling flow, airflow, liquids flow, all kind of flow. I guess electric or magnetic flow, all kinds of flows. Although this is beginning to get into actually all of them outside my expertise. I'm not I do know enough in calculus, but I do not know about the physics in itself of how things behave with flows. But we can see that this is a good way, vector fields, to show how things go. So for instance, pretend we got a vector field of this kind, and you got a particle, pretend this is water and some kind of a river, and maybe they're diverging because, and I'm making this up, I don't know, maybe there's a rock here and there's a rock here, so some of the flow here will go through, but some of the other will diverge. I don't know. So if you drop a particle here, a little paper boat here, then this shows that the paper boat will start going in this direction. And if you drop it here, it will go here. If you drop it in a particular place, it will go between the stones and so forth. Or if this is wind, yeah, we could have airflow, and maybe those are buildings. That's the way perhaps things will behave. Things could be actually more curvy. Yeah, yeah. So that's a two-dimensional vector field. We could have three-dimensional vector fields. So those are a little more complicated. So we could have f, x, y, z equals p, q, r. Those are just multivariable functions with one output, each one. And so together they make a vector. And generally you have, again, those should be straight. Each one of those vectors are straight. So you could, at this point, things may be going up, but maybe the slope as you go lower does not increase as much, and then it increases, etc. So this is a little more difficult to draw because you gotta have the dots on a three-dimensional space, and then the vectors also going in all kinds of directions. So we have a continuous, typically we have a continuous flow for every point in space. And we want to figure things out this way. So this is just a quick, super quick introduction to vector fields. Again, the way I handle them oftentimes to have a better idea of what's going on is to draw a table. How many do I put in inputs? As many as necessary to understand what's going on. And then here I would do, if I was doing an example in 3 dimensions, a particular example, then I would do the same thing. For instance, you could have, so let's write down as an example 2, f of x, y, z, let's say negative x, negative y, and keep the z the same. So what does that do? Whenever, so a point here, negative x, negative y goes in the opposite direction. So if this is x and y, we got this vector to the input. But then you got to have the reverse. So if the point is on the floor, it's going to come back to the z-axis. Now, if you have a point directly above it, it is going to go back to the z-axis, but you're going to add a height to it. So this point, this particular generic point on the floor will have coordinates x, y, 0. So it is going to point the function, the output, which is the function. So this is the input. And then the output is going to be negative x, negative y, and 0. So it's going to go directly back to the origin for any point on the plane xy there. But if you take another point directly above it, let's understand what happens to that, to this field. The vector is going to go back in the same direction towards the z-axis, but then we have a z. So for instance, if this was 2, units. It's the graph of the vector is going to go back to the z-axis, but then it is going to go up by 2. So we're going to have a long vector going up towards the z-axis. And then the vectors in between are going to just going to be going up higher as you go up. And the vectors underneath are going to go, nope. So we got a point down here. I'm going to try to erase that line because that line is there. Yeah, every point should have only one output. So you can have 2 vectors with the same input. So this one would go down a little bit, but again, towards the z-axis and so forth. And they will go, well, again, I was trying to draw on the same. There. So lower means lower. Yeah, yeah. Technically, those vectors get longer because we have to add these z. So these are they're not quite correct, and they should go down. Anyway, so this is a quick introduction of vector fields.